Okay, we're gonna begin with the static deflection. Before this, it seems like we consider the spring that connect the things on horizontal plane, and we didn't consider the effect of the gravity. Many times when we need to consider the effect of gravity, or maybe have more than one spring in the system, it's gonna have maybe pre-compression or pre-tension in the spring. And we are going to talk about the static deflection. Static deflection means in the equilibrium, the spring is not in the unstretched length. It may have some pre-compression or pre-flexion. And let's see how can we obtain the static deflection. It's very simple. For the 1 degree of freedom system, we may just draw the free body diagram of this thing. And if we define x to be positive in the downward direction, when it moves by x to the downward from the equilibrium, with the distance delta s downward positive, with the distance delta s, it means the static equilibrium. What we are going to have is the spring will create the force in the upward with magnitude k multiplied by the delta. And the mass itself should have mg. And this should be in the static equilibrium, which means the summation F in x direction need to equal to 0. The positive x direction, mg. The negative in the upward, k. Static equilibrium equal to 0. So in this simple case, we know that the static equilibrium is the equilibrium of the gravitational force and the stiffness of the spring. If the spring has high stiffness, the deformation for the static equilibrium will be small. If the spring is soft and have low value of K, it will deform with big displacement. For 1 degree of freedom, it's not difficult, right? How about when we have 2 degrees of freedom? We're gonna separate the mass M1. We're gonna have the pulley with R1 and with R2. And we're gonna have M2. What happened with M2? What happened with M2 is it only have the mg and have the tension in cable, which is unknown. For the pulley, we have the tension in the cable, and we also have another tension in cable. And for the mass M1, again, in this case, I gonna set the x1 as the coordinate to describe the system. I'm gonna select x1 as a coordinate to describe the system. And x measure from the unstretched length, x becomes 0 from unstretched length. And with the effect of the weight, it's gonna have the static deformation in the downward direction. Actually, we still don't know mass M1, M2. We don't know the radius. So we just assume the positive direction first. And finally, when we compute and we have the negative value of delta S, it means that we assume positive of x1 in the downward direction. But if delta S is negative, it means the actual value of the static deflection, the actual motion, it should go upward instead. But if we compute and we find the positive value of the delta S, it means it corresponds to the positive direction of x or the downward direction. And to define the direction, the positive direction of x1 to be downward or upward, it's not that important, but the important thing is the value, the direction of the force from the spring. The direction of the force from the spring need to correspond to what you assume. If you assume delta S to be in the positive direction of delta x1 to downward, the spring force with this static displacement and stiffness K need to be point upward. T1, tension in cable, opposite direction, the tension direction. T2 also in the tension direction. Tension means it pull the mass upward. It pull the pulley in the downward direction. What's still missing? We still don't have mg1, right? m1g. And we may begin from, let's begin from, okay, I'm gonna begin from M2. Summation F, maybe I define, it's depend on, but I'm gonna define x2 downward. Actually, if we assume x1 positive downward, x2 should be upward, but it's not that important because summation F in the x2 coordinate will be equal to 0 in the static equilibrium, which means M2G subtract by T2 equal to 0. T2 equal to M2G. How about for the pulley? For the pulley, summation of the moment about the center of the pulley should equal to 0. Now we have two reasons. For summation moment equal to 0. The first reason is it's in the equilibrium. No alpha, no angular acceleration of the pulley. The second reason is we may neglect the inertia property of the pulley, but the major reason for static equilibrium is alpha equal to 0. So maybe the pulley may have moment of inertia, but in static, alpha is 0. So summation of moment is equal to 0. And I define counterclockwise as the positive direction. So the T1 multiplied by the radius R1 subtract by T2 multiplied by the radius R2 equal to 0. Now I can form R1. No, I can form T1 in the terms of I can form T1 as 1 per R1 of M2. Wow. G R2. T1 is equal to T2 R2 divided by R1, right? And T2 is M2 multiplied by G. So the last equation I need to form is summation of force in x1 direction is equal to 0 and maybe positive downward. So we have M1G in downward direction and the spring force is in upward direction. T1 also in upward equal to 0. Okay, and you're gonna rearrange the equation by yourself, but finally the static deflection will be obtained here. We already have T1, M1G are constant, K are constant, K, and we derive the static deflection. So this is a review. When we connect spring in series, the first one has K1. The second one has K2. And we apply force. If we draw the free body diagram of spring, we're gonna have the first spring and we're gonna have the second one. And the second spring have force F to the right hand side, and when it's in equilibrium, it should have F on the opposite direction. For K1, also gonna have the force with the same magnitude on the opposite direction. If we connect spring in series, the force in the spring is equal in the series. And the total displacement, the delta X total. What happened to my pen? The delta X total need to be the combination of delta X from the first spring plus the delta X from the second spring. What we need to, for the series spring, the force equal in all the spring, and the displacement, the total displacement is the combination of displacement from the component of the spring. So the total displacement is equal to the force divided by K equivalent of the spring. We want to find the K equivalent of the spring. That are the reason from K1 and K2. If we want to combine K1 and K2 to be only a K equivalent, the total force and the total displacement, the force divided by K equivalent will equal to the total displacement, and the displacement in the spring K1 is the force in the spring K1 divided by the K of the spring K1. The force, the displacement in the spring K2 is force divided by K2. So for the series combination, what we have is 1 per K equivalent is equal to 1 per K1 plus 1 per K2. If we have n number of spring, we still can apply this. How about when the springs are connected with each other in parallel combination? For parallel combination, the delta X are equal for all the spring. Delta X are equal for all the spring. The first spring need to extend, the second one need to extend. All spring have the same displacement, and the total force, so it means the displacement, total displacement is equal to the displacement of the spring 1, is equal to the displacement of the spring 2, and also the spring n. And the force, the total force are the combination of force in the spring 1 spring 2. Maybe if we have n spring, the force generated by each component combined with each other will be the total force. And the stiffness equivalent multiplied by the displacement will be the total force. The force in the spring with K1 with the displacement delta x1 the force in the spring K2 delta x2 until Kn delta xn. But we mentioned in the above that for the parallel combination, the displacement are the same. So finally, the K equivalent should equal to K1 plus K2 for the parallel combination. And here, maybe you need to try to practice by yourself to apply this knowledge. You may combine the parallel one first to get the K equivalent, and then this and this and this are in the series. So my question is, if we have K equivalent on the left hand side, and now if we have 2K on the right hand side, do you have any idea how to combine these two springs from the left and the right hand side? Do you think the spring from the right hand side and the left hand side are connected in series or in parallel combination?
Series.
I give you another chance to think about. Okay. Before that, we come back to here. If the spring is connected in series, the force will equal along the component in the series, and the total displacement will be the combination of the displacement if the springs are in series. If the springs are parallel, delta x will be the same, and the force, total force, will be the combination of force. We come back to this example again. If we have the spring on the left and we have the spring on the right, in this case, before we answer, it's gonna be series or parallel. Do you think force on the left and the right hand side are equal, or displacement are equal?
The displacement, right?
Okay, so yeah, we set delta x. In this arrangement, x going to be positive to the right hand side, and the spring force will create the force with K delta X. If we have K to the left hand side and the spring move to the right hand side, it will create the force to the left hand side also with K multiplied by the same delta X. But the force don't need to be equal. If the mass going to the right hand side, it means maybe the force don't need to be equal. But the things that equal in this case, the constraint is the delta X and the total force on M. The total force on M, summation of force on the mass, is equal to the F by the spring on the right hand side plus by the F by the spring from the left hand side. Now, with this configuration, total force is the combination force from the right hand side and left hand side, and the displacement is the constraint. If the spring deformed by delta X, it deforms the spring on the right hand side, and also with the same magnitude, it deforms the spring to the left hand side. So when we come back to here, in which case displacement is a constraint and the force need to be combined?
The parallel one.
Yes. So be careful. Be careful. Here, delta X are the same and force need to be combined. So in this case, the spring connect with each other in parallel combination. Okay, for the second example, we have the cantilever beam and not cantilever, the pin beam. It seems like I'm not sure we can find the formula for this or not. But it seems like at the conjunction point from the left and the right part of the spring, we have the constraint delta X1. We may have K1 of the beam. We have K2 of the beam, and K1 and K2 constrained with the same vertical displacement, and both K1 and K2 generate the force in the upward direction to the box, to the spring. We may have the force F1 equal to K1 delta X, and we have the combination with the force F2 equal to K2 delta X, delta X1. And at this conjunction point, the total force is F1 plus F2, the combination of force, and maintain the same displacement. So if we are not talking about the spring, if this is not spring, just a cable, do you think the spring from the left hand side and the right hand side are connect with each other in parallel or in series? We share the same displacement and the force are combined. We share the same displacement and the force are combined.
Parallel.
Yes. So now, if we only consider the beam on the left and on the right hand side, these two springs are connected with each other in parallel arrangement, and it seems like we have K1 and K2 in parallel, and then we have another K, and we have the total displacement. And yeah, at this point we have delta x1, which is the effect of the deformation in the vertical deformation of the bar. And if this spring has another deformation, we're gonna have the total deformation. Total deformation is the deformation of the first set and the second set of the spring. And yeah, try to review by yourself maybe the how to form K1 in this case, K2 in this case. It's not that easy. I mean, I don't think I already provide you how to, because the case that I provide to you is apply the force in the center of mid span. And when we apply the force for the cantilever, the support is the cantilever. But in this case, the support is the pin. But you apply the force at the end point, here also the pin, because it can support the position, but cannot guarantee the zero deflection at the contact point. So it's pin support. So don't worry about K1, K2, but if you know K1, K2, at least you should know how to obtain K equivalent in terms of K1, K2, and K.
Should we know E and I first?
Should, yeah, of course. If in detail, you should know E, know I, and know the value of K. You should know E and I because for the beam, we usually obtain K from in the terms of EI and L. At least you should know the property. So in this problem, they give the unknown EIK. So you can answer by leave it in the form of EIK. By the way, it's still not easy because I also don't remember if we have a pin support here, and you know, how can we obtain the stiffness? Yeah. So maybe it's not easy. It's not easy. So if I want you to do, maybe if I give you K1 here, K2 here, and you don't need to think about E and I just give K1 and K2 for both sides, and you try to obtain the equivalent stiffness. In the real practice, we may need to compose the static equilibrium position to get the F1 and F2 with the constraint delta X for this case. So yeah, if the springs are connected in series and in parallel by simple form, and we can clearly see by eye, we can apply this idea. But we also have some case that maybe it's not equal to check if the springs are connected in series or in parallel, and maybe we have the transmission between those two springs. Here is the concept. How can we obtain the equivalent stiffness of the general combination of spring? And the equivalent stiffness will be obtained which correspond to the generalized coordinate. If you still remember from last week, in the system like this, we may select x1 or select y or select the theta as a generalized coordinate. And the stiffness of the spring, the K equivalent, will be derived correspond to the generalized coordinate. The idea for this is the equivalent stiffness will be derived from the potential energy of each spring, and the total potential energy will be equal to the total potential energy will be equal to the, how to say, the total potential energy. We can obtain the equivalent stiffness from the total potential energy. Let's see in the example first. In this case, we may select x or theta as a generalized coordinate. If I select x as a generalized coordinate first, maybe this is K1 and this is K2. The potential energy of the first spring, when it deforms with x, will equal to 1/2 K1 x squared. The potential energy of the spring K2 will equal to 1/2 K2 of y squared. We have the kinematic constraint. We have the kinematic constraint. Kinematic constraint means x can be described by theta and y can be described by theta, because we don't have the deformable component here. So x kinematic constraint, x equal to 3/2 r multiplied by theta. Is that? No, it's not correct. X, the radius only r. X equal to r theta. How about y? Y equal to 3/2 r and theta. So how about x and y? y equal to 3/2x, isn't it?
Yeah.
Okay, so if I want to derive the derive the potential energy in the form of x, I can have 1/2 k1 x squared plus 1/2 k2 and t/2 x squared, and the total potential energy K equivalent x squared should equal to 1/2 of K1 plus 9/4 K2 and x squared. You will do it by yourself if you want the generalized coordinate to be the theta. Help me check that 1/2 k torsional equivalent multiplied by the theta square is equal to something in the terms of k1 and k2 and theta square. Help me find this one. So the idea, the concept is very simple. You have this. You know that x can write in terms of theta. You also know that y can write in terms of theta. So in here will be k1, k2, and may have r as a parameter. And you can write the total stiffness, torsional stiffness, in terms of k1, k2, and r. The gravitational potential energy, mgh, is nothing, how to say, nothing difficult on this. Only one thing you need to carefully choose is the datum or the reference point. In this case, if you set the datum here, the pendulum can rotate with the theta. Here when the theta equal to 0, and here when the theta have the value. But if you set the datum at the pinpoint here, the potential energy will equal to mg, and the h when we measure from the datum point. So as a function of the theta, the center of gravity always beneath the datum point, and the distance that measure from the datum point to the CG always equal to L/2 cosine. When the CG is lower than the datum point, we have minus, and the distance as a function of theta gonna be L/2 cosine theta. How about if we set the datum point here? If we set the datum point at the CG position before it vibrates. We set the datum point at the CG position when the pendulum is in the vertical arrangement. The distance here is the function of the theta, and the CG position always be positive from the datum point, always be higher than the datum point, and the magnitude of this distance is also the function of the theta. And if you set the datum point here, the gravitational potential energy gonna be m g, and the h gonna be L/2 of 1 minus cosine theta. Gonna be this distance. So now for the second case, h is higher than the datum with this magnitude. In this case, h is this magnitude, but have the minus because it's lower from the datum. And we already complete the stiffness component. We already complete the stiffness component. We mentioned about the viscous damping component. If you remember, we have the spring mass damper system, and the dynamics model for this is mx dot dot plus cx dot plus kx equal to F. When we draw free body diagram of the mass, we said that if the mass is moved to the right hand side with x, the spring force will equal to kx, and we have the damper force. The magnitude is one coefficient multiplied by the velocity. If the mass has the velocity to the right hand side, the force due to the damper will point to the left hand side. On the contrary, if we move it to the left hand side and x dot has the magnitude to have the direction to the left hand side, the force generated by the damping will be on the opposite direction to the velocity. So what kind of physical things that can provide this property have the direction opposite to the velocity and have the magnitude proportional to the velocity? So mainly, the very basic thing that can provide this property is viscous fluid. Viscous fluid. When we analyze the viscous fluid, we should begin from the definition of the fluid viscosity. The fluid viscosity is equal to the shear stress divided by the shear rate. Shear rate. The shear stress is not that difficult we apply force. In this picture, it seems like we have a fluid layer, height h, and we have one plate put on the fluid. The plate has area A. The plate has area A. And we use force F to pull the plate area A on the top layer of the fluid. The shear stress is the total force divided by the area A. The force divided by the area will be the shear stress. But the shear rate, if you see here on the top layer, the fluid may have the velocity with the fully propagated velocity v. On the bottom layer of the fluid is connected to the floor. And at this point, the velocity when y equal to 0 is equal to 0. The velocity when y equal to h is equal to v of the plate. So the fluid gonna have the velocity equal to the surface. On the bottom surface, fluid velocity is 0. On the top surface, the fluid has the velocity equal to the velocity of the plate. Between the layer of the fluid, we have the linear propagation. So the velocity for each layer is equal to the height. The y divided by the h and multiplied by the v. So here at the bottom layer, y equal to 0. So u equal to 0. At the top surface, y equal to h. So u equal to v per h multiplied by y equal to h. So on the top layer, u equal to v. The shear rate is u divided by y. The shear rate is the u, which is the function of y divided by y. The shear rate is constant here because we have a constant slope. The shear rate here, if we see here, shear rate equal to u as a function of y divided by y. Actually, it's equal to the velocity divided by the height of the layer. So from the definition of the viscosity, is the stress divided by the shear rate. So can we rearrange the equation here? Oh, okay. The viscosity equal to the shear stress divided by the shear rate. So the shear stress is force divided by A. And the shear rate is equal to velocity divided by the height of the film. So finally, if we want to how to say, if we want to relate the force to the velocity, what we have is we have F and multiply by the layer height divided by velocity and A, right? So force, when we need to relate to the velocity, it's gonna be viscosity multiplied by A and divided by layer height and multiplied by the velocity. So from the definition of the fluid viscosity, we can relate the force and the velocity. And the damping coefficient. The damping coefficient is the fluid viscosity multiplied by the area and divided by the h or the height of the layer. It means that if you have one type of fluid with a fixed viscosity and you cannot change the layer height, if you increase the contact area A, you're gonna increase the damping coefficient by increase the contact area A. But if you have the same configuration of the layer height H and the area, if you can increase the fluid viscosity, you can increase the damping coefficient. The last parameter that affects the damping coefficient is the height of the film. If you increase the height of the film to be bigger than this, of course, it will allow you to have the propagation. If you increase the height, C will decrease. So here we consider only the plate on a thin film of fluid. In the actual application, maybe in the piston cylinder with a fluid inside, when we need to move the piston to the left and to the right from the fixed cylinder, the piston, when we need to move like this, the velocity of the piston will create the velocity of the fluid, but on another layer of the fluid, it fixed with a zero velocity surface. So we can create the viscous force to the system for the linear use. How about for the rotational application? For the rotational application, if you put the disc beneath the fluid, and when you rotate the disc, when we have the radius, we're gonna have the velocity of each position on the disc, depend on the radius. And the velocity will orthogonal to the radius, perpendicular to the radius, and we're gonna have the velocity. And at the surface of the disc, the fluid need to have the same speed with the disc, but on the other part near the wall of the box, or in the other part in the fluid, it don't need to have the velocity. It don't need to have the velocity. Only the contact point between the fluid molecule on the disc surface, it need to have the same velocity with the disc particle. So we can create the torsional damping coefficient to resist the angular velocity, to generate the moment as a function of angular velocity. So if we have C, or the damping coefficient, how can we obtain the damping force? How can we obtain the damping force? So it's not easy to combine the damping component. We don't have the formula to compute the equivalent C like this, like series or parallel combination, but we still can keep the idea of the energy. We still can keep the idea of the energy. So what I'm going to write is, I don't know why we don't have the summation. I'm not sure I switched the order of the slide, but the U, the work done by the non-conservative force, from initial state to the final state gonna equal to the integral of the force and the displacement, and the force gonna have the direction opposite to the velocity. The force gonna have the direction opposite to the velocity. Oh, I am sorry. In this slide, okay, I skipped the step. In this slide, we are not going to find the C equivalent. The goal is to find the C equivalent in here, but in this example, if you want to do this, you can do later. But for here, they just want us to obtain the damping force in terms of the generalized coordinate. So the generalized coordinate is the angle of the elevation, the theta. So this in the initial condition may be like this, but it can rotate. It can rotate with the angle theta. My question is, as a function of the theta and theta dot, as a function of theta and theta dot, what should be the force? What should be the force that generated by the damping component? The force have the direction opposite to the velocity. Have the direction opposite to the velocity with a constant multiplied by the magnitude of the velocity and have the opposite direction. So if this bar have the angular velocity with theta dot to the clockwise direction, have the bar has the angular velocity theta dot to the clockwise direction, the magnitude of the velocity at this point gonna be TL per 4 theta dot, and the direction gonna be in the downward direction. So the force is equal to the damping coefficient multiplied by the velocity. And the direction of the force need to be resist the direction of the linear velocity. If the bar rotates counterclockwise, at this point, velocity is going down. The force should be resist the velocity. It should go upward with the magnitude of the coefficient multiplied by the magnitude of the velocity. How about on this side? The bar rotates clockwise. So on this side, the velocity will be upward. And Vy gonna equal to L per 4 multiplied by the angular velocity. So if the velocity if go upward, the force generated by the damper should be on the opposite direction, downward, and magnitude is C multiplied by the velocity L per 4 theta dot, just like this. The C equivalent to obtain the C equivalent become for here. The idea to obtain the C equivalent is to consider the energy that dissipates from the system by the damper the energy that dissipates from the system done by the damper, the damping force is minus C x dot for each K1, C1, K2, C2. You should be careful for the unit of the C. C, the unit, it should be force divided by the velocity. The force has the unit of Newton. Velocity has the unit meter per second. So finally, the unit for the damping coefficient gonna be Newton sec per meter. So let's obtain the C equivalent from this system. The integral of the energy from the first damper multiplied by the x velocity so at any state change the work dissipated by the first damper is equal to the integral of that damping coefficient multiplied by the velocity, which may be the function of the displacement, and the integral will cover from x equal to 0 to x equal to the current x position. And for the C2, another mass, we also have y, integral from y0 to y. And C2 have the y dot and dy is coordinate. So in the system, if we want to obtain the equivalent, we may need to select the generalized coordinate that we want to. In today's class, I will try to select x as a coordinate, but I would ask you to try to use theta as a generalized coordinate and try to obtain CT or torsional damping coefficient equivalent. So for the linear case, the integral from 0 to x of C1 x dot dx, can we write the second term in the terms of x? It's not difficult, right? Because we have the kinematic relationship. We have the kinematic relationship. We know that. We know that x equal to r theta, and we know that y equal to 3/2r theta. So we know that y equal to 3/2 of x. So here, if we consider x from 0 to, if we need to change x, change dy to be x, c2 still be c2, but y dot gonna be 3/2 x dot. dy also 3/2 dx, 3/2 dx. So when we need to sum the integral, we're gonna have the integral from x equal to 0 to any x, and c1 plus 9/4 of c2 and x dot dx. So yes, this should be the C equivalent for this case. As I mentioned, if we need to change the generalized coordinate to be the theta, okay, I think let's do it together. U1 to 2 is equal to, bring this again for the first one. For the first one, minus integral from 0 to x of c1 x dot dx and 0 to y of c2 y dot dy, right? And how can we transform both x and y to theta? X equal to r theta, y equal to 3/2 r theta, right? So when we need to change from x to theta, theta will be from 0 to theta, and x dot gonna be r theta dot dx equal to r constant and d theta. How about y? When we need to change y to theta, the limit of integral will be from 0 to theta. Y dot equal to 3/2 r theta dot, and dy is equal to 3/2 r d theta. That's it. Finally, the total integral gonna be c1 r square plus 9/4 c2 r square theta dot d theta, and this is the torsional damping coefficient equivalent. Okay, the last I think, wow, should we continue next time or you want to? Okay, I think I'm gonna complete it, but if you need to leave soon, you can leave and check the rest of the content in the record. But if you can stay together, I'm gonna take for like more 10 minutes to complete this part. Before this, we talk about the equivalent stiffness and equivalent damping coefficient. For equivalent stiffness, we can obtain it from two ways. We can have the equivalent spring and have the equivalent potential energy, elastic potential energy. For the damping, we check the total energy dissipated from the system. For the equivalent system, need to equal to the energy that dissipates from the summing of individual damping component. But for the equivalent mass, the idea is similar. We are going to obtain the equivalent mass by considering the total kinetic energy of the system. By consider each component, the kinetic energy of each component and sum, it should equal to the total kinetic energy. So if we see this, we have K and we have M1 and M2. The total kinetic energy, of the mass M1 is equal to 1/2 M1 x dot square. For the pulley, if the pulley has the moment of inertia, if the pulley cannot neglect the mass, we're gonna have 1/2 I theta dot square. For the linear mass, the second one, we have 1/2 M2 and y dot square. And it depends on what should be the generalized coordinate that we select. If we select x as a generalized coordinate, x equal to r theta, y equal to 3/2 r theta, and the kinematic relationship between y and x is this. So here 1/2 M1 x dot square. The theta dot is equal to x dot per r square, right? So we have 1/2 IO, the moment of inertia about point O of the pulley, and 1/r square of x dot square. For the y component, we have y dot equal to 3/2 of x dot. So y dot square like this, and yeah, we just finalize this. So we have 1/2 of M1 plus IO per R square plus 9/4 of M2 and X dot square. So this is gonna be the equivalent mass of the system. But now we have the moment of inertia of the pulley. But if the pulley is connected to the linear mass, what if we want to obtain the equivalent moment of inertia? We still use the same concept, but we just change the generalized coordinate from x to the theta, and maybe you can try to obtain the equivalent moment of inertia by yourself. The last topic for today is what if when the spring cannot neglect the mass. Before this, we consider the mass of the box, but neglect the mass of the spring. But in many cases, when the spring is heavy and we cannot neglect the mass of the spring, what should we do? The idea is we need to consider that the kinetic energy of the spring need to equal to the total energy, So when we define one coordinate for the spring, we define U. And U is equal to 0. And U, wait, we define C or we define U. Wait a second. U when C is equal to 0, and U when C is equal to the length of the spring is equal to X. Okay, we design the coordinate C in the X direction, but X is the deformation of the spring, the total deformation of the spring. X is the total deformation of the spring. U is the deformation of the spring at the position Z measured from the initial length of the spring. So the spring has the total length of L. Z is equal to 0 at the left end of the spring, and C is equal to L on the right end of the spring. Between 0 and L, we have the value of the Z that indicate the position of that particle on the spring. The spring has the total deformation of X at the Z equal to L. At the Z equal to L, it means on the right end of the spring. The spring has deformation X But at any point between that, the spring have the deformation less than x. The deformation for any point z between 0 and L is equal to the position z divided by the total length of the spring and multiply by the total deform, total length, and the z position. It means that if the z position is far to the right hand side, it's gonna have big deformation, almost equal to x. If z is completely equal to L, the deformation gonna be the full deformation x. We need to derive the small deformation of the spring so that we can obtain the velocity of each component in the spring. So the small kinetic energy is formed by 1/2 m of the small component dm for a short length dc. A short length dc is equal to dm is equal to the very short length dc multiplied by total mass of the spring, total spring mass, divided by total spring length and multiplied by a length dc, a very short length dc. And the velocity of each small mass is equal to the velocity at that z position. And yeah, we form uz simply by this, like linear propagation. So dt is the small kinetic energy of a small part, and the total kinetic energy is equal to the integral of the dt. And the integral of this gonna be the limit of the integration when we vary the z. Z has the value of 0 on the left of the spring and limit to L on the right of the spring. And the integral of 1/2 u square, and u is equal to x/L of c, right? U is equal to x, x total deform per L total length and multiply by c, the coordinate on the spring, and square. And what next? M of the spring divided by the total length of the spring and dc. The integral of this. Okay, the constant that we can bring it out from the integral, we have 1/2 constant mass of the spring, length of the spring, constant, and the displacement, v, right? I'm sorry, u dot is equal to u dot is equal to c dot. No. It depends on the c position. U dot is equal to c per L. X dot. U dot is c per L x dot. U dot. Let's compose from 1/2 mass. Mass is m spring divided by length and small dc, and v square is u dot square. U dot square is c per L x dot square. And 1/2 m spring divided by L, and L should be L power 3, and we're gonna have x dot square, and the integral of c square dc from 0 to L, like this. And 1/2 m spring divided by L power 3 and x dot square and c power 3/3 from 0 to L. So finally, we have 1/2 of m spring divided by 3, m spring divided by 3 of x dot square. Okay, we have a long derivation, but what I want to say is just, if we know that the spring have the deformation x, the velocity x dot square. X dot square is the velocity of the mass that connect to the spring. The equivalent mass of the spring, that cannot neglect the mass is equal to the mass of the spring divided by 3. And we're gonna use it here in the last example. When we cannot neglect the mass of the spring, the total energy of this system gonna be the total energy of the system gonna be the bar. The bar has the CG and have the velocity at the CG, and the bar has the mass m. So the kinetic energy of the bar is 1/2 m v bar square. V bar is L/4 multiplied by the theta dot, will be the velocity at the CG. The effect of the rotation of the bar is 1/2 of I bar. I bar is the moment of inertia about the center of gravity of the bar, is equal to 1/12 ml square and theta dot. And the part that we just derived for the spring is the first spring here has the velocity L/4 theta dot, L/4 theta dot velocity, and the K and the spring has The spring has stiffness K and mass ms. The spring mass need to be divided by 3. That we derive the equivalent mass of the spring when we need to consider the mass, and the velocity square. This one also L per 4 theta dot. This one have L per 4 theta dot square for the velocity, linear velocity. This one also L per 4 theta dot. For here, we have 3 per 4L. So the velocity here gonna be T per 4L theta dot. So the total energy, the kinetic energy, will be formed like this. So yeah, sorry. That's all for today. I think I can share the record slide on Moodle by tonight. So let's see. Sorry, very sorry for the delay. ขอบคุณครับพวกเรา
ครับผม
ครับวันนี้พอแค่นี้ครับขอบคุณครับ
ขอบคุณครับ
ขอบคุณครับ